All right, let's talk about Euler paths and Euler circuits. So we begin with the 7 bridges of Königsberg problem. So famous mathematician Leonhard Euler wanted to show that there was no possible way that someone could create a path using these bridges and not go over the same bridge twice. All right, so here's what we mean. In this story, we can start at any of the land masses. So let me go ahead and just use a dot or a vertex to represent each of these land masses. And the idea here is he wanted to show that it is impossible to start at any of these vertices and cross every single bridge exactly once. So let's just see. So just so you know, this is water, and then these are bridges. So we can start anywhere. I will start down here for the sake of the video. You can try any of the others and see if you get a different result. So I'm going to start here. I'm going to go across the middle. I'll go ahead and do this one on the outside. I could do the same thing. I could go through the inside or the outside. Thinking maybe I'll try to go through this outside one. All right, so at this point, maybe I could try to get to this one. I'm trying to cover all the outside ones. See if that will work for me. So let me go ahead and get to this one. I'm allowed to go back. The idea is I want to try to cross every bridge once. So I'm going to go over here. All right. So at this point, if I only have one choice. I can't go back over that one or that one. I have to go to this one. Now, here's where our problem lies. If I go here, I can't cross this one or this one. If I go here, I can't cross this one. So here I'm stuck. Okay, so it is impossible to do this. And so this leads us to Euler's theorem. Before we get to Euler's theorem, we have to understand a couple of definitions. Euler path, Euler circuit. So in the past sections, we discussed what is meant by paths and circuits. So an Euler path is a path that travels every edge of a graph once and only once. Each edge must be traveled and no edge can be retraced. An Euler circuit is a circuit that travels through every edge of a graph once and only once. Like all circuits, Euler circuits must begin and end at the same circuits. So basically an Euler circuit is an Euler path that ends at the vertex you start with. So, of course, this reiterates what I just said. Every Euler circuit is an Euler path, but not every Euler path is an Euler circuit. And that leads us up to Euler's theorem. Euler's theorem has 3 parts. If a graph has 2 odd vertices, then it has at least one Euler path, but no Euler circuits. If a graph has no odd vertices, that means they're all even vertices, then it has at least one Euler circuit, which is an Euler path. An Euler circuit can start at any of the vertices. If a graph has more than 2 odd vertices, then it has no Euler path and no Euler circuit. So what we understand here, or what we can conclude here, the bottom line is each part of Euler's theorem is the number of odd vertices. And that determines whether you have Euler path, Euler circuit, or neither. So when we go to this next page, I think I'll go ahead and just do this. I was going to write like a little summary, but we'll do that when we get to our example, I think. So, of course, in order to find an Euler path or circuit that meets the requirements, we have two methods, trial and error and Fleury's algorithm. Trial and error is self-explanatory. You basically just try different things. Of course, with a small enough graph, that's doable, but when the graph is large, that's not really practical. So let's go on and just discuss Fleury's algorithm. Algorithm means that it's a process to do something. So, if Euler's theorem indicates the existence of an Euler path or circuit, one can be found using the following procedure. So you first look at your graph, at your connected graph. If you have a connected graph and it satisfies one of these two, meaning it has a Euler path or circuit, then we can move on and use Fleury's algorithm. So first, you're going to look for the odd vertices. We have two cases, basically. If you have two odd vertices, then you have an Euler path, but not an Euler circuit. And you will choose one of the two odd vertices as the starting point. If the graph has no odd vertices, so it's an Euler circuit, you can choose any vertex to start with. And of course, if you have more than two odd vertices, you have neither, so you can move on. Next, you're going to move on to the edges. So as you do this, you're going to highlight or label the edges traveled. I will often use a highlighter in practice. When you have the choice of an edge or a bridge, you always use the edge. You're only going to use the bridge when you have no alternative. Basically, once you cross that bridge, you can't go back. So it's almost like a last opportunity. All right, so given the following graph, explain whether it has an Euler path or an Euler circuit or neither. So first of all, let's remember what Euler's theorem is in a nutshell. Okay, so it's on the other page. I don't want to really keep flipping back and forth. And so I'm going to write it. I'm really going to do Euler's theorem in a nutshell. The first one said, if the graph has two odd vertices, then you have at least an Euler path, but no Euler circuit. So this will be like a little asterisk. So if you have two odd vertices, that means an Euler path, but no Euler circuit. If you have no odd vertices, then you have an Euler circuit, which by definition is an Euler path. And then lastly, more than two, so I'll do it this way, greater than two odd vertices, neither. Okay, so for the sake of the test, you can memorize Euler's theorem exactly, but I like to try to make things easier for myself. And so I try to just break it down as easy as possible. Maybe I could fit this on a note card. So regardless, the first thing I have to do is I have to find the degree of each vertex. So step one, find the degree, and really the word I'm looking for is called, there's a word for even and odd. So find the degree, really it's even or odd for each vertex. Okay. So let's do that first. I'm going to find the degree of each of these. I like to go in alphabetical order so I don't forget anything. What I'm going to do is I'm going to write the degree of each vertex in red next to the letter, and then we'll know whether it's even or odd. Okay. So A is 1, 2, 3. B is 1, 2, 3, 4. All right, so here's one of my odds. 1, 2, 3. 1, 2, 3, 4. C is 1, 2. D is 1, 2, 3. And E is 1, 2. So we have exactly 2 odd vertices. Okay. So step 2. We have 2 odd vertices, which means 2 odd vertices means Euler path, but no Euler circuit. Okay, so that's going to be part A. Part B says use Fleury's algorithm to find such a path or circuit if it exists. And they're often going to do this, not always, but typically to reduce the amount of possible correct answers. They may even tell you where to start. Okay, so we're going to start at A. We know it's an Euler path, but not a circuit, so we're not going to end at A. But we do know from the full version of Euler's theorem that if we have an Euler path, we can start and end at, here we are. If we have an Euler path, you're going to start at one of the odd vertices and end at the other one. So I've seen homework questions that are multiple choice, and I've also seen homework questions that are fill in the blank. If it's multiple choice, you can look for the multiple choice options that are circuits and throw those away because you know it can't be a circuit. You also know it has to end at D because that's the other odd vertex. So if any of the options make a circuit or end at something besides D, you can throw those away. Usually we can knock it down to 2 or 3 options, and in that case you may have to trace those 2 or 3 options. But generally what you'll find is in one of those options they skip from, say, like A to C, and that's impossible. So you'll find little tricks that work throughout the homework. So we know we got to end at D. I pretty much can do anything else, but let's just try one. Okay, so I'm going to go A, D. Now keep in mind, I have to eventually end up at D. I can hit the same vertex multiple times, but I have to cross every edge once. So let me go ahead and do that. Let me just go ahead and cross to D to get that over with. D. As I do this, I'm going to highlight each edge. I recommend this. It helps me. If I were to just try to trace over it, I may not realize, what's a traced over edge and what's not a traced over edge, but a colorful highlighter helps. So from here, I could go here or here or here. I kind of want to leave BD last or CD last because I have to end up there. But I'm going to go ahead and go to B. Again, you could have gone to C at this point. There are multiple answers to this. That's why I think you'll see a lot of multiple choice, because there's so many multiple answers that if the algorithm just says, the computer-based program allows you to just type anything, there may be too many possibilities. So A, B, D, Okay, well, I don't want to go to C because then I have to go to D. So I'm really going to go ahead and go to E or A. I'll go ahead and go to A. Again, you could have gone to E. At this point, I really have one choice. I have to go to E, I have to go to B, I have to go to C, and then go to D. So I'll go to E, and then B. Okay, let's mark that. And then C, and then D. All right. So if you use your highlighter, you'll see that everything has to be highlighted. Every edge has to be highlighted if it's a Euler circuit. We started here and we ended here.